right, so on to, I guess we just did example 1, huh? All right, so in example 2, 3, and 4 hopefully are all in this video. We'll see. Example 2, this is the summation that you are trying to evaluate, and there are 2 solutions. Well, there's a solution and then a check. So the way I wrote it out in this document is more of the check step of just making sure that you know how to plug in I equals 1. This should be an equal sign. I equals 1. Plug it in, see what you get out, plug in 2, plug it in, see what you get out, plug in 3, see what you get out, plug in 4, all the way up to 6. Add all those numbers up, you should end up with 2,912 over 81. But the book also walks you through how to do it with the formula. So the formula needs your first term, which in this case, if you plug in 1, that exponent goes to 0. 1/3 to the 0 power is 1. 1 times 24 is 24. So I know the first term is 24. I know I need 6 terms total because my lower bound is 1, my upper bound is 6, so that is a distance of 6 terms. And then my common ratio is what's in parentheses, so that's 1/3. So I know my common ratio. If you didn't know that, you could always put in different numbers and then divide them by each other and see what you get. So if you plugged them in, you'd get 24, 8, 8/3, 8/9. So if you did like 8 divided by 24, you'll see your common ratio is 1/3. Plug in all your numbers into your formula, which is the same formula from right here, because it's just a partial sum. I only need the first 6 terms added together. All right, so in example 3 and 4, I'm going to do just by walking through it, because the book does lay out the work pretty well. There's no point in me retyping it. So example 3, recall the disease outbreak from lesson 4, 8.4. This time assume the first week there are 14 cases and that each week thereafter the number of new infections increases by 25%. So if we go back, the infection is on page 522, and they're talking about the influenza epidemic of 1918. So, hey, it's kind of appropriate to know. So there are 14 cases that first week. Each week there increases by 1/4 or 25%. So sigma notation. So if we go back up to sigma notation here, I need to know the first term, which they told me is 14. I need the ratio. It's increasing by 25%. So the rate of increasing is 1.25 because you have to grow it. I have to keep the same 100%, but then add to it the 25%. So my common ratio is 1.25. And then k minus 1 is standard, just goes in there. So that's your sigma notation by the nth week. It's just expressing it. Part B is actually giving you a number then. What if the upper bound was 5 weeks? How many people would be infected? And the answer is in your book. It's about 115 people. They rounded up because you can't have 0.89 of a person. So about lets them round that up. Example 4. The maximum number of natural ancestors that you could have are 2 parents, 4 grandparents, 8 grandparents, and so on. So see the pattern, 2 times 2 is 4, 4 times 2 is 8, so the next one would be 16, the next one would be 32. So what is our common ratio in this sequence? Pause it. It's 2. Okay, so assuming that no one appears twice in your ancestral tree, so no one intermarries and you don't have a great grandpa who's also somehow your uncle or something. Where, assuming that no one appears twice in your ancestral tree past n generations, you have S sub n. Hey, we already went over that. How many generations must you go back before you have 1,000,000 natural ancestors, assuming no one appears twice? So we've done something like this with the arithmetic example, where your summation has to equal the 1,000,000. And so you're going to be setting this partial sum, because it is partial. We're only going back so far until we hit 1,000,000 people. So 1,000,000 will go in our S sub n. We don't know we know the first term. We don't know the n. So we know the rate, because that's 2, because doubling each time. We know our first term, which is 2, and I know that I need 1,000,000 over there. So then reverse engineering that, use your algebra skills. You should end up with 2 to the n equals 500,001. So, but we haven't done that yet, have we? Okay, so your book then takes the n, does the log of it, and gets 18.9. I guess we could put this in our y equals in our graphing calculators. So actually, I'll show you this on Desmos too, if no one has worked with Desmos. I have 4 seconds, so